Choice of lists. Developers often come across this question as to which list would be appropriate in a given context, linked list or array list. The short answer is that it depends upon the context. With respect to lists, here are some popular questions that are asked during the interviews. Which is the best list to use? When will you use array list versus linked list? Compare array list and linked list. When should one avoid array list or linked list? What are the drawbacks of array list or linked list? This chapter will try to provide guidance on appropriate choice of lists. Also, you'll be able to answer all the above questions. Let's understand the structure of linked list and array list. Assume that we want to store the 4 integer objects. Here's how our linked list is going to look like. So in a linked list, whenever we add an element, it adds a node. So node contains data, next, and a previous pointer. Previous pointer is not shown here for simplicity. So data pointer is going to point to the object that we need to store, and next pointer will point to the next node. So when we add 10, it is going to store the reference to this 10 in data pointer, and next will be null. When we add 99 to this, it will allocate memory for the node, and in that case next will point to that node and the data will point to 99. Similarly, as we add other elements, it will keep on allocating the nodes. The point to note here is the last node will always point to null since there is no node that is assigned, and there is always a head pointer which is pointing to the first node. So this is linked list. In case of array list, the memory allocation that happens is contiguous. So you can see here we have allocated 4 elements, 0, 1, 2, 3. These are the offsets. You can see the 0th element is pointing to integer object 10. First is pointing to integer object 99, and so on. These are offsets or indexes. Now one thing to note here is the initial capacity of an array list when nothing is specified is 8. So what happens when we try to add an element to an array which it cannot fit in the existing capacity? So in that case, it reallocates the new capacity as 150% of the original capacity plus 1, and then copies over all these references to the new array. Such a behavior is not required for linked list because you can see as and when we add the new element, the nodes will be created. So each node can be a totally different memory location, whereas in case of array list, these are contiguous memory locations. Let's see the comparison of linked list and array list. So with respect to structure, we already saw node is allocated for each new element. Each node has a reference to object, next node, and previous node. In case of array list, memory location are contiguous. With respect to capacity, the initial capacity of a linked list doesn't make sense because the nodes are allocated when a new element is added. In case of array list, the default capacity is 10, and whenever the added element cannot be fitted into the existing capacity, it will increase the capacity to 150% of the current capacity plus 1. The insertion time for adding an element is always constant in case of linked list. In case of array list, the worst case scenario will be n, because when adding an element, if it cannot be fitted into the existing capacity, it will reassign the entire array and copy over the old array to the new array. Hence, the worst case scenario is n. Removing an element from a linked list is always constant. It just removes the node. It will reassign the previous and the next node accordingly. In case of array list, the worst case situation would be n, because the removing of element can cause shift of all the next elements. When retrieving an element, the worst case scenario for linked list would be n, because it has to traverse to the linked list up to the requested element. In case of array list, it is constant. Memory. In terms of memory usage, as we looked at previously, each node has got a data pointer, previous pointer, and the next pointer. Naturally, linked list is going to take more memory, whereas with respect to array list, that is not the case. It doesn't need to store previous or next pointers. Let's look at the suitability of linked list versus array list. So in the situation where we have frequent removals or insertion needing more capacity or insertion in between the elements, or when the capacity is indeterministic, ArrayList definitely should not be used and we can go for a linked list. In the situations where random access of elements is required or the list is required to be sorted, generally sorting will mean that access to the elements will be needed in a random fashion, or the list needs to be traversed, or write once and read many times. If this is the situation, then we should definitely not use linked list, and array lists can be used in these situations. In this demo example, we are going to see the relative performance of various kinds of lists. So we'll be comparing array list with initial capacity, linked list, and copy on write array list. So copy on write array list behaves similar to array list, just that any mutation will cause copy to be created. Now we have declared list demo class. Here we have defined list as a data member. This list will be initialized through the constructor. Then we have add elements, which is trying to add elements to the list. So you can see there is a for loop and it is just adding an integer, and the iteration is the number of iterations are element count. Get element is going through the list and just doing a get operation on that. Iterate is using an iterator to iterate through the list. Finally, we have a public static method verify, which will do the following. It is creating 4 lists. One is the array list, one is the array list with initial capacity, and the initial capacity is 100k. You can see it here. Then we have linked list and copy on write array list. After that, we need to invoke each of the methods in the list demo class. So we'll be using reflection in this case. So util dot get execution time. You can look at the implementation of this, but all it tries to do is it tries to invoke the method that is being passed on the object that is being passed. These are the arguments that are required for this particular method, right? In this case, add element is taking the number of elements to be added. Also, the get execution will also record the amount of time it takes to execute, and it will return the duration in nanoseconds. Once we are done calling get execution time, it is going to return us the duration. Then we'll be creating a string which will contain the method name, the type of list, and the duration it takes. The duration is being written as nanosecond. So we are using util.nanosecond to ms to convert into millisecond. This particular string will be stored in a list. You can see that we are calling get execution time for all the types of lists: ArrayList demo, ArrayList fix demo, linked list demo, and copy on write ArrayList demo. We'll repeat the same exercise for get elements. Similarly, we'll repeat the same exercise for iterate elements method. Eventually, we'll have an array of string which contains the execution time with each of the details. And then we'll be just doing a log statement to print that. Now let's try to run this and see what the result is. So in first case, for add elements, you can see the comparison. Array list, it is taking 10 milliseconds to add 100k elements. Now you can see the array list, which is array list with the initial capacity, it is taking relatively less time, naturally because it doesn't have to do the reallocation. Now linked list is as fast as array list in terms of addition, because all it is doing is adding a node, assigning the element to it. Copy on write is taking a lot of time. You can see that it is taking almost 5.5 seconds, and the reason is every add that we are doing will cause it to mutate. So it is creating a copy of the existing lists. Hence, it is taking a lot of time. Now, when we look at get elements, you can see the comparison here. So get elements in array list fixed, and copy on write, it is almost like same. Now, in case of linked list, as you can see, it is taking almost 9.4 seconds. The reason is it has to navigate through the entire list to get that particular element that we are requesting. With respect to iterate elements, we can see relatively all of them are having same performance because all we are doing is just iterating through it. So there is no navigation that is required. So that concludes our performance comparison for ArrayList with initial capacity, linked list, and copy on write ArrayList.